have with us Dr. Gregory, who is the Director of Technology at Energy Impact Partners. EIP is a fund that is focused on backing tough technologies for solving for decarbonization. At EIP, Dr. Gregory focuses on driving excellence in technical due diligence and building novel technology-centric investment thesis. Prior to EIP, he served at ARPA in the US Department of Energy, where he helped develop new R&D programs and also deployed over 40 million in funding for climate and energy technologies. While there, he initiated the agency's first program in direct air and ocean capture and supported efforts on tough to decarbonize sectors such as industrial heat and aviation. His technical career includes previous postings in engineering, automotive, climate control, and battery cooling systems, as well as performing research on desalination systems. He holds a PhD from MIT and a BSc summa cum laude from Case Western Reserve, both in mechanical engineering. He has additionally published over 20 peer-reviewed journal articles in thermal sciences, water, and energy systems. Dr. Gregory, welcome to our Fireside series.
Well, thank you.
So Energy Impact Partners talks about its focus on deep decarbonization. Could you help us understand a little bit more about it?
Yeah, so the way I think about deep decarbonization is it means getting to net zero greenhouse gas emissions across the entire economy. And so, as you all know, there's something like 30 to 35 gigatons of CO2 produced annually across the globe, and another 10 or 15 beyond that in non-CO2 greenhouse gases. And so for us to reach our sort of IPCC defined climate goals, we've got to get to net zero by somewhere around mid-century. And so deep decarbonization at EIP is looking across the whole economy to find ways to get to net zero. And I think our take is basically that unsurprisingly and unfamiliarly to everybody on this audience, it's needed, and it's needed soon. And it's going to be one of the largest mobilizations of capital and economic opportunity of our generation.
Right. And so while breakthrough technologies are the ones with the highest ability to limit and subsequently reduce emissions, the path from proving the concept in a lab to actually being impactful at scale is often very, very long. How would some of the technologies that you see look at this path to commercialization, and what are typically the challenges that a deep tech startup faces when it is looking to commercialize?
Yeah, that's a really broad question. I think there are so many hurdles that one faces in going from sort of the lab to commercialization. But I think you need a lot of different things to get there, right? You need the right team around the table of both technical folks and commercial folks. You need capital, and as you noted, you probably need quite a bit of capital, at least relative to maybe a software startup, because hard tech is hard, right? And you go through all of the challenges of building things for the first time, and that comes inevitably with knots and bumps and everything else along the way that you have to solve. So I'm happy to go into any of those things in more detail, but I think at the very early stage where we invest, one of the biggest challenges we find in starting companies even is matching really strong commercial founders with strong technical founders. So oftentimes we have great commercial founders and we have great technical founders, and unfortunately those two networks don't talk as often as they should. So even from the get-go, getting the right people around the table is I think a big challenge.
Right. And, this is a challenge across the board, getting folks who are very smart commercially and getting them to partner with folks who speak often a different language when it comes to technology and commercialization. How do we get the two to not just work together, but also kind of align on vision, align on capital spends? How has that played out in your experience?
Yeah, I think venture organizations, investment organizations, but also the broader sort of climate community has a role to play in convening. I've seen universities, I've seen governments, I've seen NGOs put on sort of pitch to match events where folks can try to build those connections and try to, as you say, kind of learn the other party's language, to be able to begin to build those connections and hopefully build better teams that will be more likely to succeed in the long run. So I think, focused events on building that network and building those connections are a great way to do that.
Right. Coming back to some of the breakthrough technologies we're seeing, one of the key focus areas on decarbonization is on energy transition itself, and one of the biggest challenges that we're seeing in transitioning electricity away from fossil fuels is that generation tends to be seasonal, not very predictable, sporadic even, and there are lots of factors that are just very difficult to plan for. How are you looking at technologies that are aiming to solve for this particular bottleneck?
Yeah, that's a great question. I mean, decarbonizing the power grid is in many ways the first step in decarbonizing the rest of the economy. And so having clean power when you want it, that's affordable, is really, really important. And as you said, renewables are one technology that can meet the clean power goal at lower and lower costs, especially as what we've seen over in recent decades, that the cost of renewables has really dropped. But as you say, the power doesn't come when the sun doesn't shine or when the wind doesn't blow, and so you need something to balance that. And so energy storage is a crucial part of decarbonization and the energy storage. And so we've been looking all across the sort of battery landscape and even non-battery type energy storage systems that we think can play a role. The way we think about energy storage is to segment the market kind of into various durations. So duration is usually thought of as the sort of length of time that an energy storage system discharges or provides power back to the grid. And so already today, we're seeing things like lithium ion on the grid, providing shorter duration, maybe up to 4 hours of energy storage, and doing other things and providing other services to the grid as well. And so going forward, as more variable renewable energy comes onto the grid, we're going to need more so-called longer duration energy storage systems. And so you look at things like novel battery chemistries that can discharge for longer durations. You look at things like flow batteries. You look at things like maybe thermomechanical type storage systems, be they compressed air storage, liquefied air storage, or maybe even using another gas. And so there's a whole suite of technologies out there that I think will be needed in some form or another to provide longer and longer duration storage. The other, and this isn't the only path, right? Renewables plus storage. So I think when you're thinking about a decarbonized grid, there's a need for clean, firm, cheap baseload power as well. And so we're looking strongly into geothermal and enhanced geothermal and such things that can meet that demand. So I'm happy to talk about some of those topics as well.
Sure. So speaking of geothermal, and maybe while we're talking about alternatives to just renewables, would also love to hear your views on where we are in our ability to commercialize nuclear fusion. And then coming back to geothermal, what are the challenges that geothermal would face in scaling up?
Yeah. So I think before you had sort of asked about sort of technology timelines and maybe what's just over the horizon and what's a little bit further out. I think nuclear fusion is really exciting because obviously if everything pans out as we all hope and expect, then the result is nearly limitless clean power, right? I think from a scientific perspective, the recent announcement by the National Ignition Facility in California was extremely exciting because it showed us that ignition is possible. There's still a ways to go, as everybody who will have read the news around this understands. There's still a ways to go in terms of getting to a true reactor, but we're pretty excited about the amount of money, attention, and scientific progress that's been made.
Right. So if you had to hazard a guess around how long before we actually have commercially viable power derived from fusion, what does that horizon look like? And also, what else needs to fall in place for it to happen?
Yeah, I mean, I think what needs to fall in place for it to happen is you've got to get more of these reactor designs to a sort of break-even condition, and not just sort of a scientific break-even where sort of the energy coming out of the core reaction is greater than the energy going into it, but from a sort of wall plug or engineering perspective where you need to get more energy out of the reactor than is going into the whole reactor, the whole system itself, right? And probably a lot more energy, right? So I think that will certainly need to happen. Beyond that, folks talk a lot about what else needs to happen in the sort of supporting ecosystem. If we're going to use DT fuel, deuterium tritium fuel, then there needs to be systems for tritium handling and so forth. And even once the reactor itself produces enough heat output such that you're well beyond energy break even, you've got to turn that heat into electricity. So there's a lot of complicated and challenging engineering questions to be solved in that window as well.
And each of those engineering problems is a large commercial outcome in itself.
Certainly, I think there are plenty of large engineering commercial outcomes to come from fusion.
Right. And how would geothermal stack up versus this?
Geothermal, I think, is a really interesting case. As you know, conventional geothermal is something that we know how to exploit today and have exploited. I think where the R&D community is going and what's really exciting to think about is things like enhanced geothermal, which might involve going deeper than today's geothermal technologies. And the reason that's really exciting is because more or less, the deeper you go, the hotter it gets. And the hotter it gets, the more power you can get out of a fixed amount of heat going into your system. So the other thing that's really exciting about enhanced geothermal relative to traditional is traditional geothermal, you're kind of looking for a hot crack, if you will, that's near the surface where you can find a hot geofluid that's close enough to the surface that you can extract some heat out of it. And some of these enhanced geothermal technologies that really go much deeper and might even involve creating permeability and porosity in the subsurface are less geographically constrained because they're not relying on finding some sort of crack with geofluid that pops up to the surface. So the broader resource, the deeper resource, the hotter resource, all of those things are really exciting things that I think can be unlocked with good technology.
Got it. On the electrification side, particularly regarding transport, we're seeing that this is emerging as the most popular means, especially for shorter range transportation. We're seeing a lot of innovation in batteries to push that range, innovation across charging time, energy density, range, temperature management. One of the trickiest problems that we might encounter here is around access to minerals that are crucial to most of the batteries that we're seeing. And when you layer this with the associated geopolitical tensions, the problem just gets further exacerbated. Would love to understand what you are seeing across the innovation landscape in this context.
Yeah, I think that's a really important question. If decarbonizing light duty vehicles in particular, as you say, continues to be by battery electrification, I think as most of us expect, then we're going to need a lot more minerals to create the batteries. It's lithium ion, of course, uses lithium itself as the fundamental um, uh, sort of electrochemically active species in the battery. But the cathode materials in particular also use a number of metals, some of which are in short supply or in, concentrated in particular parts of the world. So I'll talk about lithium a little bit first and then maybe get into the others. So, lithium is right now today basically mined mostly in hard rock form in places like Australia and from brines in places across South America. And basically those two areas have the highest concentration of lithium around the globe. And of course, the higher the concentration of the resource in general, the easier it is to access. So the thing is, though, there is lithium elsewhere in the world, both in this sort of hard rock form, which can be extracted one way, and in brines, which can be extracted in other ways. And what we see as a particularly interesting space is a technology area called direct lithium extraction, which is a sort of more engineered way of removing lithium from brines, and hopefully much lower concentration brines, meaning a larger resource than what's just in South America. And so I think there's a number of innovations there that are taking place and will continue to take place around novel ways to selectively remove lithium from lower and lower concentration brines. So I'm hopeful that there's a good solution to be had for lithium. On sort of the rest of the battery, the cathode materials in particular, you think about things like nickel and manganese and cobalt. Cobalt is quite a challenging one. It's geographically concentrated in terms of its resource. And so engineers and scientists have been working over time to slowly sort of reduce the amount of cobalt that's required in batteries. And of course, recently we've seen other cathode chemistries come to the fore and increase in popularity, like lithium iron phosphate, that maybe don't have the same energy density as an NMC type cathode, but for many applications might just be good enough. So I think there's a lot of paths forward there that will help us get around mineral supply constraints as well.
Right. And how would say a sodium ion battery stack up versus a lithium ion battery in terms of performance and use cases?
Sodium ion is not something that I've spent a lot of time with personally. I think one of the challenges you might face in bringing in any really sort of non-lithium chemistry into the fold is that we already have a big sort of growing supply chain around lithium ion batteries. And so anything else that you might wish to replace lithium ion with is going to have all that more of a challenge in kind of getting integrated into the supply chain. The other advantage with lithium in particular is, the further you go up the periodic table, right, the lighter the elements are, and that kind of relates back to energy density. And so if energy density is everything, which maybe isn't everything, but it's certainly pretty important for transportation applications, then generally lighter elements are going to be better, right? And lithium's pretty light.
Fair. So continuing on, the thread on the transportation use case itself, for true long range use cases, we're talking, continental shipping, aviation. We're likely to need other innovation to scale up as well. This could be around hydrogen, methanols, biofuels. Additionally, if one looks beyond switching, there's also mode switching that is being proposed. Could you walk us through, some of the innovations that you're seeing in the space, and what are the hard roadblocks that these are encountering and that other tech co-founders could look at solving for?
Yeah. So, it's a great question. And I think that, we were just talking a little bit about the importance of energy density. And I think nowhere is energy density more important than in something like aviation, where weight is everything in the aircraft. So the range of an aircraft, the sort of fundamental first principles, simple model for aircraft range is basically a very, very strong function of weight. And so this is why, in aircraft, you work to use lighter and lighter materials, and that has happened over time in aircraft, and weight is really everything. So if you're going to fly an aircraft in a decarbonized way, you really, really need an energy dense fuel. And I think energy dense in that sense means, yes, by weight, which hydrogen certainly stacks up pretty well there, but also by volume, because we've got to fit this thing into an airframe. And so it's for me personally, it's hard to see a solution near term that doesn't involve some sort of liquid fuel for aviation. So I think we're pretty excited about sustainable aviation and synthetic hydrocarbons that would be made from clean hydrogen and green CO2. But further out, I think there is a path for alternatives here as well, specifically in shorter range aircraft. Maybe if you've got a lot more higher energy density batteries, there's a path for sort of battery electrification there. Maybe with certain sort of fuel cell hybrid drivetrains, there's a way to use a cleaner, easy to make, but slightly lower energy density fuel there. And of course, if folks can solve the challenges with hydrogen's volumetric energy density, then there may well be a solution technically there as well. So I think this is all to say that I think energy density for aviation is a critically important metric, and there's lots of room for innovation in decarbonizing that space.
Right. And how do you see the cost curves moving there with respect to green hydrogen?
Yeah, so I think I'm based in the US, and so my views are a little bit US centric in that regard. But one of the things that I'm sure you've all heard about that happened in the US is the passage of the Inflation Reduction Act, which put in a $3 per kilogram clean hydrogen tax credit in the US. And so that I think is pretty exciting. I think clean hydrogen, whether it be steam methane reforming with CCS or methane pyrolysis or electrolysis, was already on a cost down trajectory, but having policy support that can take out some of that added expense near term and kind of help deployment and begin that innovation flywheel that says deployment begets lower costs is really important and really exciting. So I think clean hydrogen is one of the technologies that I would put in the just over the horizon bucket in terms of economic competitiveness and availability.
Got it. And there's a lot of talk about mode switching, right? Do you actually look at vertical takeoff? Do you actually look at hydrofoils? Can you walk us through some of the mode changing innovations that you're seeing as well?
Yeah, that's a great question as well. I mean, I think we've certainly seen a suite of folks looking at air taxis and other such things. Hydrofoils, I've seen a handful of companies looking at using maybe foiling for water taxis and things like that. And I think, we should take the attitude that all hands should be on deck, right? There's room for any solution that can be cost competitive and low carbon and affordable.
Right. Now, like you said, it's going to be all hands on deck, and we'll need to see what works and what works faster. Um, Green shoots, no pun intended, are being seen in a lot of use cases in power and transport. And then we have our hard to abate industries like steel and cement. Steel alone would account for about 8% emissions globally. And let's face it, we are going to continue to need our built environment, and and we will only grow from here on. And so, how does one look at solutions that can reduce the embedded emissions in these industries?
Yeah. Um, Steel and other sort of heavy industries, as you say, are really massive sources of greenhouse gas emissions. And steel in particular is quite challenging because the emissions come not only from burning a fuel to provide the high temperature heat required to get sort of the chemical fundamental chemistry to go, but also from CO2 that results from the chemistry itself, these sort of process emissions. So it's not as simple as finding a high temperature, low carbon, affordable heat source. There's more to it than that. And so there's a few things that are looking quite promising in steel. One is the use of hydrogen as a reductant, so replacing metallurgical coke with hydrogen, which acts as a reducing agent and reduces iron ore into iron as part of the steel making process. And the other one, we're invested in a company called Boston Metal that's working on an alternative solution that uses a technology called molten oxide electrolysis that uses electricity directly to reduce iron ore into molten iron as part of the steel making process. And so I think, as you say, steel making is a really important and challenging and tough to decarbonize part of the economy. I'm glad that we see these clean solutions, hydrogen and molten oxide electrolysis, as things that are just over the horizon.
And a lot of times, the organizations or the stakeholders that need to adopt are their understanding of breakthrough technologies and their willingness to absorb breakthrough technologies, because they believe a new one just might right be over the horizon, tends to be low. And so how should a technology company really navigate that challenge and work with such stakeholders and reduce their fear of technology risk?
I think the proof is in the pudding, right? I think the more companies can show that these technologies work, they're cost competitive, they're reliable, the more they can demonstrate these things at larger and larger scales. My hope is that will lead to greater and greater adoption. So I really do think the proof is in the pudding. That's much easier said than done, as everybody on this call, I'm sure, certainly knows. But demonstration is, I think, and hope, the technical, at least, key to success.
Right. You mentioned Boston Metal. Would love to understand what they are doing and how they are tackling the problem of emissions in the steel industry.
Yeah, so as I mentioned, they use a technology called molten oxide electrolysis, which basically is a high temperature electrolysis cell that takes iron oxide, which is the sort of mined form of iron ore, and reduces it into iron and oxygen, liquid iron, in fact, and oxygen, and that liquid iron can then go into sort of downstream steps for making steel. And that's really exciting because because first of all, you're taking the use of metallurgical coke, which is the carbon that results in a CO2 emission, entirely out of the process. And so your only byproduct is pure oxygen. And it's electrified as well, which means you can couple that process with with clean electricity. And so the result is an emissions-free from a process perspective, from a process emissions and a heating emissions perspective, an emissions-free steel product that goes through no intermediate steps and is something that I think could be a big part of the future steel economy.
Right. There's a lot of activity that's happening in the carbon management space as well, right from measuring and monitoring to capture and storage. Um, would love to understand how you're seeing the storage and capture space evolve, and what are some of the more promising and close to horizon technologies that you're seeing for capture and storage.
Yeah. Capture and storage is also an exciting space. And I think that the two things that are sort of really exciting for me personally are carbon mineralization and direct air capture. So mineralization more on the storage side. So for those who may not be familiar with carbon mineralization, it's the notion of taking captured CO2 and reacting it with specific types of minerals to form generally carbonate phases. And the reason that's really exciting is because when you form something like a carbonate, that is a type of material that's thermodynamically, that's physically stable for very, very long periods of time. And so that means that any sort of CO2 capture and storage that you do, right, you don't have to worry about it releasing, right? It is a thermodynamically stable form of carbon storage, and in fact mimics nature's carbon cycle. And so that's something I think on the storage side that we've seen a lot of innovation in recent years, and is something that's really exciting because it represents a really highly permanent, if I can say that phrase, but very long-lasting form of carbon storage. So that's something we're really excited about on the storage side. On the capture side, I'm sure everybody has seen a lot of the buzz around direct air capture, and of course that's exciting because it represents it is the removal of CO2 directly from the atmosphere. So going after exactly the thing that's causing the problem in the first place in a very direct way. And I think you get into, when you talk about direct air capture, oftentimes folks get into discussions about direct air capture versus mitigation and avoiding the emissions in the first place versus point source capture. And I think we need to be wary of all of these. We need to be aware of all of these things. But if you look at the IPCC projections for the 2-degree scenarios, about 2/3 of the 2-degree scenarios go through the zero line in emissions in the second half of the century. That is to say that global net emissions, go below zero in the second half of the century. And so the only way that you can get net emissions below zero is with carbon removal technologies like direct air capture. So I think, yes, we should avoid and mitigate everywhere we possibly can. We should do point source everywhere we possibly can. But DAC is going to be a part of this picture, or carbon removal is going to be a part of this picture too, if we want to limit global average temperature rise to below 2C. And in fact, like I said, 2/3 of those 2C scenarios go through the zero line. All of the 1.5-degree scenarios go through the zero line. So carbon removal, I think, is going to be a critical part of our future.
As you said, there's a lot of buzz around DAC. How realistically speaking, how far from commercial deployment are we, especially in terms of affordability and what it's going to cost to capture CO2 directly from the air?
Yeah, it's a great question. I mean, I think the short version is that some companies already have commercial deployments today. So Climeworks, I believe, has the largest number of facilities that are sort of in the 1,000 ton per year size that are actively capturing CO2 and selling it to buyers today. So in that sense, there are commercial facilities, and at the scale that we need to affect the climate. No, we're still building towards that. In terms of the cost curve, I think we're certainly in the multi-hundreds of dollars per ton today. Climeworks, I think, sells for in the high hundreds of dollars per ton. And I think there's a lot of room to come down that cost curve, and I'm pretty hopeful there. A lot of folks have a sort of $100 per ton target in mind, and certainly with certain tax credits in the US and certain carbon prices that we see around the world, that would be an attractive number if it were achievable. But I think there's really quite a bit of improvement to be had on these systems. And I'll talk about energy consumption is just one portion of the overall cost. I think there are many aspects of direct air capture costs that are coming down and need to continue to come down. But energy consumption is one that I think there's particularly quite a bit of room for improvement on. A lot of systems today are even 5 to 10 times, even more than 10 times the sort of minimum energy prescribed by physics. And so I think there's that tells us alone that there's a lot of room for improvement on that front, and we're seeing folks make strides in that direction.
So you talked about tax credits under the policy regime, and how we're seeing a lot of cross-border tax on carbon as well. And so decarbonization is something that will require not just tech breakthroughs, but also a lot of support of policy and adequate capital. These are three stakeholders that tend to speak a very different language. And so how does one get them all aligned? And particularly when it comes to helping them understand the potential of technology, what the path ahead looks like, even setting expectations on timelines that the technologies would require for commercialization. You've seen some of this play out in your pre-EIP life as well. I would love to hear about some examples where you can talk about how technology folks should navigate this.
Yeah, I mean, I think here we are back to the question of language again, and commercial folks and tech folks and policy folks speaking different languages. I think that the solution to that is really having the right people in the room, and having a broad representation of stakeholders across capital markets, technology, innovation ecosystems, policy spaces, and making sure that folks are really deliberate about how they communicate with each other to understand what state of the art is and where we need to go. And so certainly that was something we did quite a bit of in my DOE days. It's very common for these agencies to have workshops where academic stakeholders, industrial stakeholders come together with folks from the government, and folks discuss questions around, where are we today, and what will it take for us to get where we need to go. And I think those sort of interactions are critical in us all meeting our shared goals around climate.
Dr. Gray, we have a few questions that have come into our chat box. I'll read out a few of them, and we could take them one by one. So what's your view on the pace of innovation in low carbon cement, and how far are we from commercial production? What barriers exist in widespread adoption?
Yeah, great question. So I think there's a number of things going on in cement and concrete more broadly. We have companies like Sublime Systems, for example, is in our portfolio, looking at making a truly carbon neutral cement, which in cement, of course, is the biggest, is the part of concrete production with the largest greenhouse gas footprint. We also see things like, supplementary cementitious materials that might allow you to reduce the amount of Portland cement in your concrete mixture, and thereby, if they're made in a low greenhouse gas way, thereby reduce the total carbon footprint of the concrete that's used. So I think we're seeing a lot of innovation along that front. I think the challenge, as with so many of these things that are kind of core to our economy, is being able to produce them in a cost competitive way. Fortunately, I think we are seeing policy support on that front as well, with green building and green building material mandates coming down the pipe in certain places, with certainly things like the 45Q carbon capture tax credit. If you were to put CCS on a traditional cement making plant and so forth. So I think cost is certainly a barrier, but it's coming down, and we're having policy support in the right direction that I think, again, can kind of kick off that innovation flywheel to put us in the right direction.
We had a question on the hydrogen space. It's inefficient and super expensive to move hydrogen in its own by ships. Is that correct? And how does one solve for that?
Yeah, I think transport of hydrogen. That's a great question. Transport of hydrogen is a great topic, and it's something, again, that's pretty challenging to do. And so I think we're seeing a number of again, innovation pathways on that front for how do you store and transport hydrogen in an energy efficient and cost effective way. We're seeing everything from sort of solid sorbents that can absorb bits of hydrogen onto their surfaces, to using chemical hydrogen carriers like methanol or like ammonia that more easily liquefy, and so are more easy to convey across distances and store in tanks and other forms. And so I think that's as we use more hydrogen, which I think we all think we need to, especially for some of these difficult to abate sectors, probably won't always be able to produce it where you need to use it. And so storing it and transporting it is going to be an important part of the future decarbonized economy.
Right. How realistic is direct air capture going to be, especially with carbon prices hovering around $100 per ton, and recycling that carbon is likely to give 2 or 3 times the value, and also back to fossil fuels. What's your view on the whole recovery and remining element for carbon?
I'm not sure if I'm understanding the second half of that question very well, but I'll try to answer the first half around the realisticness of direct air capture. I think what it comes back to me is it's not as bad as you think from an engineering perspective. I think a lot of chemical engineers might look at something like direct air capture and say, hey, wait a second, the concentration of CO2 in the air is a couple orders of magnitude less than it is in a natural gas flue stack, and that's hard enough. So this sounds really hard, and I think it is hard. I don't mean to circumvent or blow over the challenges, but I think it's not as bad as you think. And two of the things that often come up are, well, because it's low concentration, you have to move a lot of air, and that's true. You do have to move a lot of air, but we move a lot of air in other sectors of our economy as well. So I think we're not moving more air than we do through a jet fleet or through a fleet of wind turbines or things like that, right? So it's moving a lot of air, but it's not amounts of air that we don't know how to move, right? And the second thing that comes up is, lower concentration means higher energy consumption. And again, it's higher energy consumption than a point source capture system, but it's maybe not as bad as you might think, because it turns out that the energy required to do direct air capture and carbon capture generally kind of scales with the log of the concentration. Forgive me, I'm getting a little bit wonky here, but it scales with the log of the concentration. So if you reduce the concentration of CO2 from which you're trying to remove carbon from a mixture by 2 orders of magnitude. The energy only goes up by a factor of 2, not by 2 orders of magnitude, because of that fundamental physics scaling. So again, forgive me for going a little bit wonky there, but the point is, I think it's more feasible than you think.
Right. We have one more question here. One of the most difficult areas to decarbonize is industrial heat due to huge variation in temperatures as well as different industrial setups. How are you seeing this space? Heat pumps and heat storage are some of the directions, but these appear to not have even started in the real sense.
Yeah. Also a great question. Yes, industrial heat accounts for a large fraction of industrial emissions, and industrial emissions themselves are something like a third of global emissions. So this is a critical thing, a critical sector to decarbonize. And as the questioner indicated, it's challenging because heat is delivered at a variety of different temperatures. And the things that we typically use to provide those heat, fossil fuels, burn at very high temperatures, so they can serve all of that demand. It's also challenging economically because heat is cheap. The cost of heat is the cost of fuel plus your capex to deliver it, and it turns out the capex is pretty cheap. And in many facilities, it's old capex that's been depreciated. So it's really challenging economically to find something that might be a low carbon solution that might be competitive. So there's a couple things that I think are up to meet the challenge. One is industrial heat pumps. I think that's going to be a solution for obviously the lower temperature range, because as you go higher in temperature, the performance of the system drops off, so you don't get as much of an advantage. But the great thing about industrial heat pumps and heat pumps in general is that you get more units of high temperature heat out than electricity units that you put in, because you take some lower temperature heat from the surroundings. And so the magic of heat pumps is that that sort of coefficient of performance, or COP effect, that allows you to get more high temperature heat output than electricity that you put in, is the economic lever that allows that to be a cost-effective source of clean industrial heat. So for the low temperatures and the smaller scales, I think industrial heat pumps are really, really exciting, and I anticipate we'll see more there going forward. In the sort of mid and higher temperature range, it's more challenging. And one of the solutions that we think is really interesting, we're invested in a company called Rondo, which uses basically is high temperature thermal energy storage, which means they take electricity in and they heat a storage medium that's essentially stores that heat at a very high temperature, and then discharges that thermal battery on demand when a process needs it. And their system can operate at very high temperatures, and so therefore can store and operate at very high temperatures, and so therefore can deliver heat at all across the temperature range. And because it's using storage as the medium, it can charge with cheap electrons. And so that means charging with cheap electrons plus a cheap storage medium means cheap delivered heat, which is the key to success.
Right. We'll just close with one last question, and this goes back to marrying technology and business. As a venture capital investor, how are you looking at long gestation bets like nuclear fusion, especially given that there is a timeline on returning back capital?
Yeah, I think it's a great question. We at EIP have a lot of veterans from the clean tech 1.0 so-called era, the first wave of clean tech innovation, and so we know that innovations, really true breakthrough hard innovations, are hard and take time, and we're set up to take those risks, and hopefully we all get through to the other side as well. So.
Right. That brings me to the end of our session. Thank you, Dr. Greg, for really wonderful insights, and I'm sure folks are taking away great ideas and insights from the session. I really appreciate having you here.
Thank you for having me. It's been a pleasure to be with you.